All right, so today we're going to continue looking at X-ray photons, and we're going to have a look at some of their properties. Right, so X-ray photons are made in what we call an X-ray tube, and what I've listed here is just a few things we need to know about the X-ray tube. Okay, so we need to know a few things, and let's start with up the top, we've got a high voltage energy supply. So this diagram's a little bit confusing the first time you look at it, but hopefully it's not too bad once we take a bit of a closer look. So our high voltage energy supply is so we can accelerate our electrons. We remember that. What we've got is two really key pieces to this high voltage energy supply. We have the filament and the source. Okay, now we call this the target, we call that the anode, and we call this the cathode. All right, now the anode is positive, and the cathode is negative. Okay, now the cathode to start with is the source of electrons. All right, so when we heat this cathode up, electrons are emitted. Okay, or they can kind of leak out. So we heat this filament up really hot, and it's also negatively charged. Now, what happens is our positive charge is so large that it can kind of pull these electrons out and towards it. All right. So this is the anode and the cathode and the high voltage supply. So as we're accelerated towards the anode, when we get there, we hit this. You can see there's a bit of a solid block there. That's our target, and it's made of a really dense metal. So we saw last time we need a really dense nucleus to do that. So we choose metal because it has a really dense nucleus, so we can get those Bremsstrahlung photons produced. So that's what the source is. So we accelerate, we hit the source, and that's how we produce X-rays. Now, a really, really important part of this is we need to have like a glass envelope around the tube. Okay, that's so it can be evacuated. Okay, which means no air. Because if we had air in between here, our electrons, as they went across, they'd hit the air and it'd be a bit messy. We need them to go straight across, so we need a vacuum in there. So that's all good. Now, what we've got is we crash into here, and our X-rays are produced, and we've got a window. All right, so we come out of the window, and we get those images that we saw last time. But what else happens is our copper block, because not all of it is turned into X-rays. Some of it is just crashes and turns into heat. We need to remove the heat. All right, and the way we do that is we pump a coolant around there, and that coolant removes the heat from this block so it doesn't get too hot. Okay, so this is the basic setup of an X-ray tube. All right, so we're going to introduce a couple of terms now, and we're going to look at the intensity again. So the intensity means like how many. Okay. Now the intensity is decreased, so there becomes less as they pass through matter by scattering and absorption, and that makes sense. So if we send some X-rays into our arm to have a picture, when they hit our arm, some of them are going to be absorbed. My arm's going to absorb them. Some of them are just going to be scattered, so hit into random directions by my arm. Now, another way to say decreased is this word attenuated, and this is a really important one. So attenuated means decreased. We also have these words scattering. Scattering means our X-ray comes in, it hits something, and it kind of just scatters off in a different direction. Absorption means our X-ray comes in, and our material just absorbs it, eats it. There's no more photon. All right, so attenuation, that's the reduction of X-rays, and it depends on three things. The first one is the density of the tissue. So different tissues have different density. Bone is really dense, it's really packed together, but skin or soft tissue like muscle is less packed together. So our bones stop a lot of X-rays, and that's why X-rays are really good for looking at bones, because we see that on the picture really well. All right, and X-rays are attenuated more by a higher density like bone. Now the next thing that we have to have a look at is the thickness of the tissue. And that makes sense. So if we're shining an X-ray through a really thick piece of material, more of it is going to be scattered and absorbed than if we go through a thin material. So an increase in thickness increases attenuation because there's more chance of being absorbed. And the last thing that impacts the attenuation is the elements that the tissue is made from. All right. So X-rays, they interact with atoms and molecules. So if we have a bigger molecule, the more chance we have to be absorbed. Okay. So so basically the atomic number increases the attenuation. So that's why if you've ever had an X-ray and you've been sitting there, they might have put a piece of metal, a piece of lead over your lap or on your chest or somewhere, because the lead has a really high atomic number and it stops a lot of those X-ray photons. So it protects you from those other X-ray photons that are coming out. All right, now we've got this other word, penetrating power. So to take effective photos or X-rays, we need to control the attenuation. So sometimes if we want to look at bones, we want to penetrate a little bit further than if we want to look at blood vessels or organs. So what we say is if we want low attenuation, so we want low scattering, low absorption, we have to have high penetrating power. We have to penetrate more. And if we want to have a high attenuation, so we want those muscles and organs to absorb our photons, we have to have a low penetrating power. Now these are called hard and soft X-rays, and I think that's pretty obvious in this case. Now the last thing we want to look at is exposure time. So once we've chosen how hard we want the X-rays to be, we want it to penetrate, we have to decide on the exposure time. So this is just like a photo. If you want to have a look at a moving target on a photo, you want to take a really quick exposure, just get a snapshot of that time. If you want to have a look at something that's not moving, like a mountain, if you're a photographer, you can have a really large exposure time so you get all of that light in. And it's the same here. So basically, the longer exposure time, the bigger the chance to produce a blurry image. And that's about it for exposure time. So I've posed two questions. Do you want a long exposure with soft X-rays or a short exposure with hard X-rays? A bit of a question. Have a think about it. If you can't work it out, come ask me. But which one do you think is best? So there is a reason and there is a link there. Now, just the last thing with exposure time. If we want a longer time, what we need is, if we have a look back at our tube, we need more of these X-rays produced. So we need more of these electrons to go across over a longer time. So what we say is we need an increase in tube current. So remember, current is how many electrons we have flowing. So an increase in tube current. And with our penetrating power, so if we need more powerful X-rays, what we say is we need to increase the tube voltage. Okay, so penetrating power is related to tube voltage, and our exposure time is related to tube current. So I've just got a bit of a summary here, have a read through, and that's about it for now. So thank you.